Retrieval Augmented Generation, or RAG for short, is a commonly used solution to instruct LLM for generating answers from unseen or proprietary data. However, various experiments have shown that the vanilla RAG is sometimes not sufficient, and different tricks have been developed to enhance the performance of vanilla RAG. One such technique is HyDE, short for Hypothetical Document Embeddings. Given a query, the hypothetical document embeddings first zero-shot prompts an instruction following LLM to generate a fake hypothetical answer document that captures relevant textual patterns from the initial query. In practice, this is done 5 times. Then it encodes each hypothetical document into an embedding vector and averages them. The resulting single embedding can be used to search for matching documents in vector store. These retrieved documents can then be used in a downstream pipeline like RAG. HyDE can be very useful when the performance of retrieval stage is not good in your RAG pipeline. In this video, I will explain how to implement the hypothetical document embedding algorithm to improve the RAG app retrieval performance. We will use open source LLM Llama 3.1 freely available through Grok API for building our examples. So without further ado, let's get started with the coding part. Alright, so I have included the total code for this tutorial in this Jupyter notebook, and I will include a link to it into the description so you can download and follow along. At the beginning of the notebook, I have included a link to the research paper of the algorithm. Then I have highlighted how it works. So there is a small description of how the algorithm works and why it is useful. So what are the benefits of using this algorithm? Then I have highlighted the important sections of this tutorial. So first of all, we will load the data. So for this tutorial, I have decided to use the Form 10K report of Meta, which was filed for year 2023. It's around 150 pages PDF report and it's publicly available. So after loading the data, loading the PDF pages, we are splitting it into the chunks, and those chunks will be added to the vector store. And we will also visualize these chunks or our data set by projecting them onto the lower dimension. So we will reduce the dimensionality of the embeddings of these chunks using the UMAP algorithm, and then we will visualize it as a scatter chart. So we can see like where particular documents and query and all that are. In the next section, I have included a sample example of how to query the vector store. So what the documents are retrieved with the normal query. Then we implement the HyDE algorithm where we generate a hypothetical document answer and retrieve the documents based on it. And there we visualize the original query and the retrieved document. And then there is another version of HyDE. So actually this one is the original HyDE algorithm where we generate the 5 answers to the actual query and generate embeddings of those answers and average them, and then retrieve the documents based on that average embedding. And then in the 6th section, I have created a simple RAG application which checks that what is the performance of the retrieved documents. So for the given query, if we retrieve documents only based on query using the HyDE algorithm with 1 answer and the 5 answer, so what is the performance of 3 different cases? That will be shown in this RAG performance section. Next, I have highlighted the important libraries, Python libraries that we'll be using in this tutorial. So you will need to install Grok, LangChain and ChromaDB. So ChromaDB is our vector store. It's an open source vector store. So in the first cell, I am simply loading the environment variable. So I have kept the Grok API key in the current directory in the .env file, and that's what I am loading over here. So Grok API key variable has our API key. Then I am importing ChromaDB, our vector store, and printing the version. So this is the version that we are going to use for this tutorial. And then in the next cell, I am creating Grok client. So Grok client with the Grok API key. So this client will be used to talk to the Grok API to access our LLM. So for creating this Grok API key, which we loaded earlier, you need to log into console.grok.com and create an API key. Now there are many different LLMs available from Grok. So recently launched Llama 3.2 and its various versions, Llama 3.1 and its various versions, Gamma, and so many different LLMs are available. For this tutorial, I'm going to use Llama 3.1 70 billion versatile version. So this one we are going to use for this tutorial. So in this first section, we are loading our PDF file. So I have kept this Meta 10K 2023 PDF report in the current directory, and we are loading it using the PyPDF Python library. And over here, as you can see, I am loading the individual pages. So total number of pages are 147 pages present in this report. And Form 10K is a comprehensive report filed annually by a publicly traded company about its financial performance and is required by the US Securities and Exchange Commission. So that report filed by Meta we are going to use for this tutorial. And here is a sample first page which we loaded. So after loading the report, so 147 pages, in this section we are splitting that pages further into chunks. So for that we are using the recursive character text splitter class, which is available from langchain.textsplitter. So we are creating an instance of that class over here. So this will be used to split the pages further based on the character counts. So I have kept the chunk size to be around 1000. So for each chunk around 1000 character will be kept, and there will be overlap of 25 characters. And these are the separators. So first there will be separation happen on these two new line characters, then new line characters, and so on. So that will be the precedence of these separators. And once we have created the splitter object, we can call the split text method on it. And over there we need to provide the total string which will be split into the chunks. So I have combined all the pages into one string and separated the pages by these two new line characters. And that total string, which is the total text of the PDF, is given to the split text. And that will create the chunks. And the next I have printed the total chunks. So our report of nearly 147 pages is now divided into 634 chunks of text. And here is a sample chunk. So these chunks will be added to the vector store. So in the second section, we will be adding the text chunks that we created in the previous section into our vector store. And as I said earlier, we will be using a ChromaDB vector store for this tutorial. So first of all, we need to create a persistent client to interact with the ChromaDB, and persistent client will store the collection or the vector store to the disk. And for that I have given path which is meta 10k. So the folder will be created by this name, and inside of that there will be a SQLite file where the embeddings of the documents will be stored, the embedding of the chunks. So that will be the chroma client. And then in the next cell I have declared the embedding function. So the LLM that we will be using to create embeddings of the chunks. So for this tutorial I have decided to use this Distill Roberta version 1. So this LLM we will use to create embeddings of the query and chunks and everything. And this LLM is available through Sentence Transformer Python library, and we can access it using this class Sentence Transformer Embedding function, which is available through chromadb.utils.embedding functions. So we are creating an instance of that class with the model name, and this Distill Roberta object is a function which we can call to create embedding of any text chunks. And in the next cell I am creating a collection using our chroma client. So collection is an concept from ChromaDB, and inside of collection we store the embeddings and the documents. So name of that collection I have kept as a meta annual report, and there is a small metadata about that collection. An embedding function I have set to Distill Roberta. So whenever we add document to this collection, this Distill Roberta function will be used to create embedding of those documents, the text chunks. And the Distill Roberta outputs an embedding of size around 768 length. And then I have set parameter get or create to true. So if this collection is already existing, because we are creating persistent collection, if this collection is already existing, then this setting this parameter won't create a new one. It will retrieve the existing one, because we don't want to keep on adding the text chunks to the collection again and again. So that's how you can create collection. And then in this cell, So in this 2.2 section, I am adding the documents to this collection. So when you're running this code on your computer, and if you already called this cell once, then do not call it again, because it will add the same documents again to the persistent collection. So call this only once. And collection.add method can be used to add documents to the collection. So we can provide documents, so character, text, split. So these are the chunks, 634 chunks that we created from our 150 pages, around 150 pages. And apart from documents, we need to provide IDs as well. So I'm simply looping through the indexes, or we can say the length of the character text splits, and simply adding this string split 1, split 2, and so on, which will be the ID for the individual documents. And as you can see, the collection.count method call returns 634, because those many chunks were added to the collection. And when these documents are added, their embeddings will be created using this distill-roberta function. So that's how you can add text chunks to the collection. Now in this section 2.3, I am visualizing the text chunks. So this visualization will be useful when we implement the HyDE algorithm to see where the query and the retrieve documents are. So we are creating a scatter chart of the text chunks, and over here we will plot. So these are all the text chunks, 634, and we will plot the query and the retrieve documents over here, so we can see where they are. And for creating this chart, I am using a UMAP algorithm. So UMAP is a dimensionality reduction algorithm, and we can use it to reduce the dimensionality of our embeddings to the 2-dimension. So first of all, I am retrieving embeddings of all the documents. So by calling this method collection.get, you can retrieve embeddings of all the documents, and that's what I am doing over here. This embeddings has embeddings of all the documents. So all the 634 chunks embeddings will be over here in this embeddings variable. Then we are creating an instance of UMAP, calling fit on it with the embeddings, this embeddings, and this will create a UMAP projector object. And then in the next cell, so in the next code, I have created a function. This function takes as input any embeddings and this UMAP projector, and then it creates the projected embeddings for this input embeddings. So I'm calling this function over here with the UMAP projector object, trained one, and our embeddings, the dataset embeddings. So this projected dataset embeddings now will have a dimension of 634 by 2. So it went from 634 by 768 to 634 by 2. So that's the projected dataset. And then I have simply created a scatter chart of that projected dataset. So as you can see, projected dataset embeddings of 0, which will be x axis, and the projected embedding of 1 will be the y axis, and the gray is the color used for each of this chunk. So that's how you can represent the total data set. So in this third section, I am simply querying our vector store with the given input query without any algorithm to see what kind of documents it's retrieved. So I'm going to use this query for our tutorial, that what are the risk factors for the company. So what are the risk factors for the meta, and then we can query our collection using this query method. And over there is a parameter named query text where we can provide our query. I have set n results to 10 because I want to retrieve the 10 relevant text chunks or 10 relevant documents from our collection, and I have asked it to include the original documents and their embeddings. So that's the results. Results is a dictionary, and these values are included in that dictionary. So in this retrieve documents one, I am retrieving the documents which are retrieved using this query, and then I have printed those documents one by one. So as you can see, the first document is about the risk factor. The second one, I'm not sure, but should be about the risk. Yeah, the third one is about risk factors, as you can see. So those are the 10 documents retrieved which I have stored in this variable retrieve documents one, and this one is the default query result. So we haven't applied the hide algorithm yet. So let's go ahead and visualize these query results. So first of all, this retrieve docs embeddings, I have retrieved the embeddings of all the retrieve docs, the 10 documents that we retrieve. And then I have created the embedding of our query using this distilled robot embedding function. So the retrieve documents and query embeddings are present. And then using this project embedding function, which we had declared earlier, I have created the project embeddings of the query and this retrieve documents. So we projected them from 768 dimension to 2 dimension. So we can visualize them on our original data set. And that's what I am doing over here. So I'm plotting a scatter chart. So over here, first we are plotting the original data set. As you can see, gray are all the original text chunks, 634. Then I am plotting the query embedding. So as you can see, it's plotted with the red dot. So this one is the query embedding. And then I'm plotting the embeddings of the retrieve documents, the projected retrieve embeddings over here, as you can see, and they are represented with this cross marker and lime color. And over here, as you can see, the 10 documents are plotted as a cross, and you can see from the result that a few of the documents are near to the query, but quite a few others are far away, and one of them is quite far away. So yeah, that's the result by using a original query to retrieve documents. So let's go ahead and implement hide algorithm, where we generate a hypothetical answer and use that to retrieve documents. Alright, so in this fourth section, we have our first implementation of hide algorithm. So for that, I have declared a simple function named generate answer. And if you remember, I have explained how hide algorithm works at the beginning of the tutorial in the intro. And we generate a sample answer to the input query, and we use that sample answers embedding to retrieve documents. So this function is used to generate a sample answer to the user query. So as you can see, this function takes as input query and the model name. So model name is the llama 3.170 billion by default. And then I have set the messages. So this is the standard message format which will be used to call the LLM. So first is the system message, which says that you are a helpful expert financial research assistant. Provide an example brief answer to the given question that might be found in a document like an annual report. So we are giving a system instruction to generate a helpful answer, brief answer, which will be answering the query based on what answer generally found in an annual report. And then we are giving the user role with the query. And then I'm simply calling the chat API, the Grok API, using the client chat completions create method with the model and messages, and retrieving the response and returning it. So we can call this function generate answer with our query, which is that what are the risk factors of the company, the query which we defined earlier. And then here is the generated answer I have printed. So these are the risk factors. So these are risk factors generally found in majority of the company's report. So now the embedding of this particular answer will be generated, and that will be used to retrieve the relevant text chunks. So I feel that this will give better results than simply giving the query that what are the risk factors of the company, because there are many words over here. As you can see, these words will help to find the useful chunks compared to only single line query. So over here, I am generating the embedding of our answer using this distilled robot embedding function we declared. And then I am querying our collection with this embedding, answer embeddings. So there is a parameter query embeddings which we can use to query the collection based on the embeddings. So in the previous section, we had queried our collection based on the text, but you can also query based on embeddings. And even if you give query text with the generated answer, internally it will generate an embedding using digital robota, and then we'll retrieve the relevant documents. We are retrieving 10 documents. The other parameters are same like earlier. So that's the result, and that's our retrieve documents too. So this is the HyDE document with only one answer. So those documents are retrieved, and here are the documents that are retrieved. So this is almost same as our previous calls. And as you can see, the document seems to be explaining about the risk. So let's go ahead and visualize them. That way we will get a better idea of the retrieved documents. So again, I have retrieved the embeddings over here, and then the query embedding is generated, and this 3 line of code projects the embedding. So original query, then answer embeddings, and then retrieve documents embeddings all are projected to the 2 dimension using our UMAP algorithm, dimensionality reduction algorithm, and then we are visualizing it. So as you can see, the original query is plotted with this red dot, which is over here, and the generated answer comes out to be somewhere over here, and all the retrieved documents, as you can see this time, are near to the generated answer. So unlike our previous quiz where all the documents retrieved, only some of them were near to the query, but quite a few were outside of the query, outside of the neighborhood of the query. So let me show you. So as you can see, only few were over here, and then others were quite far away, as you can see. But with the HyDE algorithm, as you can see, majority of documents are in the neighborhood. So it seems to be doing a good job at retrieving documents. So in this 5th section, we have implemented the original version of the HyDE algorithm according to the paper. So in the previous section, we generated only one answer and used its embedding to retrieve the relevant documents. But in this section, we are generating 5 answers. So as you can see, I'm looping through this range 5 times and then calling this function, and then we are printing the answers as well. So 5 answers are generated, 5 different answers, and the embeddings of all this will be calculated and averaged. So that's what I have done in this next section. Using digital robota, I have created embeddings of this generated answer, 5 answers, and those are stored in this array, numpy array. And as you can see, the dimensionality of this array is 5 by 768 because 5 answers. And then I am averaging them over here. So now the final embedding is 768. So these average embeddings will now be used to retrieve relevant documents. And that's what I am doing in the next cell. So I am querying our collection with this parameter query embedding set to the average embeddings. And again, we are retrieving 10 documents with the documents and their embeddings. So those documents are stored in this retrieve documents 3. So, and then I am plotting them. So it seems that this first document is the same in majority of the cases, but others will be definitely different. And then we are visualizing them. So I am again creating the projected embeddings from the original embeddings. So original query embeddings, answer embeddings, average answer embeddings, and the retrieve documents embeddings. All are projected to 2 dimension using this project embeddings function that we created. And then we are visualizing them over here on the scatter plot. And as you can see, this red dot is our original query, and this orange dots are the generated answer, and this purple dot is average of those generated answers, and all other crosses are the retrieved documents. And it seems that this version is also doing a good job at retrieving the documents, as majority of the documents are near to this average generated answer. Alright, so now that we have implemented the 2 different versions of HyDE algorithm and retrieve the relevant documents based on that, let's go ahead and build a sample RAG application which generates a response based on the retrieved documents. So over here I have created a sample function, RAG function. It takes as input query, and the retrieved documents, and based on that query and retrieved documents, it generates an answer. So first of all, it creates an information variable that will be combining all the retrieved documents. So first of all the retrieved documents will be combined by this two new line characters in this variable information. And then there are messages. So standard system message is over here, that you are an expert financial research assistant. Your user are asking questions about information contained in annual report, and you will be given user's query and the relevant information from the annual report. Answer the user's question using only this information. So we will be giving the query in this user role. We will be giving the query and this information. So this information is the relevant documents, and then we are calling the API, Grok API, and retrieving the response. So over here, the first one is simple rack. So this is based on only query. So I'm calling the rack function with the query, and retrieved documents are retrieved documents 1. So this is from the first section where we retrieve the relevant documents based on only query and not HyDE implementation. And this is the output. As you can see, it generated 4 points and then few sub points. So this is the answer based on only retrieved documents based on query only. So in the next section, I'm using the HyDE algorithm, which was based on only one answer, and we retrieved the documents based on that generated answers embedding. So again, calling the rack function with retrieved documents 2. So this is from that section. And as you can see from the output, this output seems to be more detailed compared to our previous output. It's quite detailed, and there are many points covered compared to our previous output, which was based on only query. And this one is based on the sample generated answer and embedding of that answer. So let's go ahead and try the main version of the HyDE algorithm, where we had retrieved documents based on the average embeddings of 5 generated answer. So that was present in this variable name retrieved documents 3. And as you can see from this answer is also quite detailed. It's covering quite many points compared to the first answer. It's covering 5 points and many sub points. And as you can see, the first answer had only 4 points and few sub points. So as you can see, both the versions of HyDE are doing quite well compared to the sending only simple query to your RAG application. Alright, so that's how you can implement hypothetical document embeddings algorithm. If you have any doubts or any questions, then please feel free to let me know in the comment section, and see you next time.